This is slightly more complicated. Here, the fuel is not just one component, but multiple components. Okay, so in the earlier cases, in this earlier case where we were looking at ethanol, ethanol is typically not found as a fossil fuel. Okay, it's not found in any oil well. You have to produce this synthetically, meaning you produce it either from sugar cane or from corn, but you produce it through chemical process. So we get more or less pure ethanol, and we can have this sort of combustion happening within the engine or wherever you want the combustion to happen. But when we talk about burning fuels, fossil fuels typically, whether it's natural gas or it's gasoline or diesel, basically it's not one component but a mixture of components. All right. So here we have been provided a certain natural gas which has this molar analysis. Okay, it contains 80.6% methane CH4, 5.4% C2H6, 1.87% C3H8, 1.6% C4H10, as well as some amount of nitrogen. Okay, so these are all different hydrocarbon fuels, right? Methane, ethane, propane, butane. These are all fuels that can go and undergo combustion all by themselves. Okay, but since this is something that we are getting it from the ground, it's sort of a mixture that we get. Of course, this quantity of the mixture is going to be different depending on the location you pick it up, right? If you're extracting gas from some location in Saudi Arabia, it's going to be different than what you extracted from some other country. Even within the country itself, there are going to be variations. So this is something that we need to sort of, this is another practical example where we are dealing with the fuel, which is itself a mixture. Okay. So here for this particular fuel mixture, we are burning this natural gas, and you're basically burning it with dry air, which basically means dry air simply means oxygen plus 3.76 nitrogen. Okay, you're burning it with dry air, which gives you the products on a molar analysis. Sorry, which sorry. So when you burn this natural gas with dry air, you get the product whose molar analysis on a dry basis gives you the following. It gives you CO2, CO, oxygen, and N2. Okay, so in this particular case, we need to calculate the air fuel ratio on a molar basis and the percentage of theoretical air based on the information that's provided to us. Okay, so here if you look on the product side, you have CO2, CO, oxygen, and nitrogen. Okay, these are the dry products. You also have to add water to it. But just by looking at these products, you can say that the combustion is incomplete simply because we see CO in the products, and it is incomplete because of improper mixing, since we have free oxygen on the product side. Okay, there is some amount of oxygen, but it did not combine with CO to form CO2. This indicates that the mixing was not done well. Okay, or there was not enough time for mixing to happen. So here, when we are trying to solve this question, the first part is to calculate air fuel ratio on the molar basis. So what this requires you to do is to first write a balanced chemical equation. So you need to write something like fuel plus some moles of air giving rise to the products, right? CO2 plus CO plus O2 plus nitrogen plus H2O. So this is what we need to actually write in. Okay, and the idea is once you write this equation and once you balance it, then you just need to write the value of A. Okay, A, if you're using 1 mole of fuel, then A by 1 is the air fuel ratio on a molar basis that we are trying to determine. So for you to get the air fuel ratio, first part is to do the balancing part, right? And the way you're going to write the balanced chemical equation is the same way that we did before. Okay, so you write fuel on one side, fuel plus air, which are the reactants, giving rise to the products. The products are already provided to you. Okay, now when we are writing this equation, to start off with, we can simply assume that we have 1 kilomole of fuel, right? And then we can write the equation. So if you assume 1 kilomole of fuel, we can write this as 0.8062 times 0.8062 CH4 plus 0.0541 C2H6 plus methane plus propane and so on, right? Till nitrogen. So this all part right here, this entire thing is nothing but the fuel. So when you're writing the equation, we need fuel plus air. Okay, so A times air. This part is air, and this is giving rise to B times the dry products, whose analysis we have been provided, plus water. You should never miss water here. Okay, whenever you have hydrogen in the fuel, such as here, in each of these we have hydrogen in there, hydrogen atom in there. Whenever you have hydrogen, you will surely form water. Okay, it will not show up in the dry product analysis though. So this is what we have here. And the way to solve this is basically the same method that we used before. So again, you have to apply conservation of mass for each of the atoms. Okay, we have carbon atom, hydrogen atom, oxygen, as well as nitrogen atoms. So we don't have to, sort of recheck. We could just pick any three of these, maybe CHO, and then try to determine the quantities of A, B, and C. Once you find the values, the problem is already solved. Okay, so let's see how you apply the conservation of mass for carbon. So here we have, molecules where you have C2, C3, and so on. So you got to be careful in how you pick it up. All right. So on the fuel side, carbon is there in all of these, right? It's there in methane, ethane, propane, as well as butane. On the reactant side, on the product side, it's only there in two compounds. It's only there in CO2 as well as in CO. So here, let's start by writing the amount of carbon on the product side. So it's B times 0.078 to indicate the carbon atoms in CO2 plus 0.002 to indicate the carbon atoms in CO. Okay, this is going to be equal to the carbon atom in methane, which is 0.8062 plus 2 times, because there are two carbon atoms in C2H6, 2 times 0.0541, 2 times 0.0541 plus 3 times 0.0187 plus 4 times 0.016. Okay, now here the only unknown is B. All other things are just numbers. So when you solve for it, the value for B comes out to be 12.931. So we have found this one right here. Now we need to find a couple more, and we're going to do that by applying the mass balance again for hydrogen and oxygen. Okay, so same way you can apply the mass balance for hydrogen. So hydrogen is only available in water on the product side, so that's 2C. Okay, it's going to be equal to 4 times this number in methane, 6 times this number in ethane, 8 times this number in propane, plus 10 times this number in butane. Okay, so this is what it is. When you solve for it, C comes out to be 1.93. So this is the value for the water. Okay, so this is 1.93. Now we can do an atom balance for oxygen. You could also do it for nitrogen, but let's say we're just doing it for oxygen. So again, on the right hand side, on the reactant side, it appears oxygen appears only in air. It's not there in any of the fuel like we had earlier. So you just have 2A, and 2A will be equal to the oxygen in several compounds in the product side. So it's there in CO2, CO, as well as free oxygen plus water. So there are two atoms here. So 2 times 0.078 plus 0.002 in CO plus 2 times 0.07, right? 2 times this number, whole thing times 12.931, okay, times B, right? Plus 1.93 plus C, which is what we just determined. So here you get the value for A. A comes out to be 2.892. So now it's just a matter of plugging the numbers there. Okay, so you plug in the numbers into this equation. This is the fuel plus A times air plus it's going to be equal to B times the dry products plus C times water. Okay, so this is what we are writing here. Now we just need to get the air fuel ratio. All right, air fuel ratio on a molar basis. So that's moles of air divided by moles of fuel. So here we are having 2.892 times 4.76 moles of air. Okay, 4.76 because 3.76 from nitrogen plus 1 mole from oxygen. Okay, so that's what the air is composed of. So that's the quantity of air that we're having. On the other side, fuel, we just have 1 kilomole. So these are the quantities for kilomoles of air by kilomoles of fuel. So it comes out to be 13.77 kilomole of fuel, kilomole air by kilomole fuel. So basically, in the above equation, what we are seeing is that for 1 1 kilomole of fuel, we need 13.77 kilomole of air to get the following products as per the above reaction. Okay. All right. Any question here? Anything that's not so clear or requires more explanation? You guys have a pop quiz at the end of it, so if you have questions, do ask. All right, looks like things are clear then.
Doctor,
Yes, go ahead.
I am from the other section. Can I take the pop quiz?
All right, message me at the end of it and I'll add you.
Thank you.
Okay, welcome. So now let's do this. Let's actually go ahead and calculate the dew point temperature as well. Now, dew point temperature has not been asked in this question. The reason I want to calculate it here is simply because it's there in your homework and I want to show you how to do that. Okay. So typically this is also what's asked here. So once you have solved once you have written down the balance equation, you have determined the air fuel ratio. The question also says determine the dew point temperature of combustion products in degrees Celsius at 1 bar. Okay. Now these are the combustion products, right? These 3 plus water vapor. So when we talk about the dew point temperature, the only thing that's going to convert from vapor to liquid is water, nothing else, right? All the others will continue to remain as a gas. So determining dew point temperature basically means finding out the dew point temperature for water. Okay, and the dew point temperature, if you recall, is nothing but the temperature at which the vapor will start condensing, and this happens once it reaches the saturation pressure at the partial vapor pressure of interest. Okay, so if you know the quantity of water vapor in the product, then if you find out the partial pressure of water vapor in the product, now if you cool it down to the temperature which is equal to the saturation temperature at this pressure, then at that below that temperature the condensation will start to happen. Okay, so this is simply that we just need to calculate the saturation temperature here. Now for us to calculate the saturation temperature, we need the partial pressure of water vapor. Okay, and here we just know the total pressure. All right, so now by using the definition of partial pressure of water vapor is simply equal to the mole fraction of water vapor, let me write YV, times the total pressure. Okay, now the total pressure is given as 1 bar. The only thing that we need to calculate is the mole fraction YV, okay, for water vapor, and this is simply equal to the number of moles of water vapor divided by total number of moles. Okay, now again we're just looking at the product side, nothing else. So we're looking at water vapor on the product side. So looking at this, we can just see that the number of moles of water is simply 1.93. So number of moles is 1.93 for water vapor. The total number of moles, however, would be equal to 1.93 plus the number of moles for all these components for the dry products. Okay. Now the dry product analysis is typically done in a way such that the sum of all all these different gases, right? It should come out to be 1. So it's basically when you add it up, it's 100%. So it should be 1 here. Okay. So it's 1.93 plus 12.931 times 1. So when you add this up, well, of course, this comes out to be 14.86. So basically, you're getting 1.93 by 14.86, which is equal to 0.129. Okay, so basically here, the partial pressure of water vapor is equal to the mole fraction 0.129 times 1 bar. So it's 0.129 bar. Okay, so this is what we obtained. Now, once you know the partial pressure of water vapor, we just need to determine the saturation temperature at this partial pressure, which is very easy. Just go to table A3 and then look up the saturation temperature at these pressures. You may have to do some interpolation, or you could also take some approximation. So if you go to the table A3, you will see that this partial pressure corresponds to Tsat of about 50 degrees Celsius. So here the dew point temperature is 50 degrees Celsius. Okay, so this is how you determine the dew point temperature for combustion products. I mean, you just have to determine the partial pressure for water, and once you do it, you already know the temperature at below which the water will start to condense. Okay. All right. Any questions here with respect to the dew point temperature calculation? All right, looks like there are no questions. So then let's go ahead and start solving the last part of the problem. The last part of the problem is the calculation of percentage theoretical air. Okay. Now, if you have to calculate the percentage theoretical air, basically, I mean, what happens is that theoretical air is the minimum amount of air that's needed for complete combustion. Okay, so percentage theoretical air tells us whether it's excess air or deficiency of air. Okay, so if it's, let's say, anything more than 100% theoretical air, that means we have excess oxygen or excess air in the fuel air mixture, right, on the reactant side. If you have less than 100% theoretical air, that means that you have lack of oxygen on the reactant side. So now by looking at the products, right, by looking at the products that we have, can you tell us if we have if we should be getting more than 100% theoretical air, or should we be getting less than 100% theoretical air in this question? So, I mean, what I'm trying to ask you was, do we have excess air in the fuel air mixture that we provided, or is it less than what was needed? The combustion products give you an idea about whether there was excess air or less air.
Excess air.
Okay. Excellent. And why do you say there was excess air?
Because we have O2.
Perfect. Whenever you see oxygen on the product side, that means you have excess air, right? You had enough air for the reaction to occur, but it just did not occur. And we said that's the reason we said the combustion is incomplete because of lack of mixing here, or incomplete mixing here. So if you have excess air, that means that you have more than the air that's needed for complete combustion. Okay. So basically, what the answer that we're going to get is we have more than 100% theoretical air. Now we don't know exactly how much, right? To calculate exactly how much, we need to calculate how much would you classify as theoretical air. Okay, what is the air-fuel ratio required for theoretical air? Now for that to happen, what we need to do is we need to again take the fuel. Okay, and we just don't know how much air is needed, right, for complete combustion. So we'll have to again balance out the equation. So you write fuel plus some A times air is going to give the products. Now this time we know exactly what the products are. They're going to be only CO2 plus H2, and of course nitrogen, because it does not take part in the in the reaction. So you have B, C, and D here. All right. So here basically you again have to balance out this equation by applying the atom balance for each of these and get the value for A. Okay. Now once you do that, the balanced chemical equation would come out to be in this way. So this is this entire thing is the fuel plus some mole fraction of air. Here once you balance it out, it comes out to be 2. Okay, and it's going to be equal to the product side. On the product, you just have CO2 and H2 apart from nitrogen. Okay, so this, of course, this is for obtaining this, you have to do the same atom balance procedure that I just explained and that we did in the previous classes. So the whole point of this is to obtain this part right here. Okay, what is the amount of air that's needed? So here, by looking at this balanced chemical equation, we can write the theoretical air fuel ratio, meaning the minimum amount of air needed for complete combustion, is simply equal to 2 times 4.76, right? This is what we have here, 2 times 4.76 by 1, so 9.52. So this is the minimum amount of air that's needed for complete combustion. Okay, now to calculate the percentage theoretical air, we just need to look at the actual air fuel ratio, which is 13.77, which we just calculated, divided by the minimum amount of air needed for complete combustion, which is 9.52. Okay, we got it here by balancing out the equation. Now, as we expected, we are having excess air to start off with, so this ratio is more than 100%. It comes out to be 145%.